Hey, AP Physics students, this is Mr. Heinrich, and we're looking at another progress check. We're looking at Unit 1, Number 2. Let's get right into it. So we've got two cars. Car A is going to the positive direction at an acceleration of A naught. Car B is heading to the left at an acceleration, half that, A naught divided by 2. This text just reiterates what I just said, and if we look at Part A, we see Figure 2 shows the position of Car A at times 1 second, 2 seconds, 3 seconds, and 4 seconds. And it's clear that the car is accelerating because we're covering more and more distance with every passing second, which is proof that the car is speeding up. So what they want from us is to draw a corresponding dot pattern to represent the position of car B at those same 4 times. So let's get into how we prove that out. So looking at my paper here, we've got the car going, again, this is car A, and it's going one box, then 4 boxes, 9 boxes, and then finally 16 boxes, which is at the very end over here. And so now we need to figure out what car B is doing. Now, if you just said to yourself, well, that's half the acceleration, and so we should cover half the distance, you'd be correct. But we need an equation that proves that to us because we're trying to learn how to pass this test coming up. So if I look at the following expression, displacement is equal to V naught T plus 1/2 AT squared. That's the equation I write for both cars. Now, I haven't personalized either equation yet for either car, but if you're wondering why this is the right equation, well, they gave us some specific information, right? They gave us A naught for car A and A naught divided by 2 for car B. So they gave us acceleration. They gave us times 1, 2, 3, 4 seconds. They also told us that it starts from rest. So we know initial velocity is 0. And we know we're looking for the distance car B goes relative to car A. Now I'm going to write distance because they refer to it as distance in part B, and that'll just help us out. I know displacement is different than distance, but we'll put D in just for the sake of the question. All right, now let's personalize each one of these cars. So I'm going to call this one distance D that car A goes, and that would be an initial velocity of 0, 0 times T, we cross it out, 1/2 A naught, because that's the acceleration of car A, times T squared. Jumping over to car B, I would write dB, the distance car B goes, equals, again, the initial velocity for car B is 0, so this whole thing crosses out, 1/2 A naught divided by 2 T squared. So if I want to know how far this one goes relative to this one, we're talking about a ratio. So what I'm going to set up is exactly that. What is dB compared to dA? And we can simply put in the two expressions. That's A naught divided by 2. And then I put in 1/2 A naught T squared. We know that they travel for the same amount of time, so it shouldn't surprise you that we cross that out. And the halves cross out also. But check this out. The A naught actually crosses out, which makes this thing formally come out to 1/2 over 1/12, so it's 1/2. So what is this ratio telling us? It's telling us that when we look at car B relative to car A, we're going to go half the distance. And that's really the answer. So if I apply that reasoning to each one of these dots, we get this. Half of one box would be half a box. Half of 4 boxes would be 2 boxes. Half of 9 boxes would be 4.5 boxes. So 1, 2, 3, 4.5. And then finally, half of 16 boxes would be 8 boxes. And that's it. Part A is done. Let's go on to part B. So part B is going to ask us to come up with the total distance between the two cars after a time they designate as T naught. Let's check it out. Starting with an appropriate kinematic equation, derive an expression for the distance between the two cars after time T naught in terms of A naught. So they want our answer to have both T naught and A naught involved. And the good news is we already have the expressions we need to make this thing happen. And they're sitting right here. So if I'm looking for the total distance, well, total means addition. So I'd say distance total would simply be dA plus dB. That's it. And I can put in these two terms. dA was 1/2 A naught T squared plus dB 1/2 A naught divided by 2 T squared. And we almost have like terms here. So let's simplify this side a little bit more. I'd say 1/2 A naught T squared plus these two twos multiply and we get 1/4 A naught T squared. And I'm really close. I see that I have a 4 in the denominator and a 2, so I'm going to get a common denominator, multiply top and bottom by 2, and you get 4 and 2 right there. So 2/4 A naught T squared. Oh. It's at a time called T naught. I forgot to put those knots in. Okay, now 2/4 plus 1/4, we would get a total of 3/4 A naught T naught squared. And that's the answer. That would be the total distance after a time T naught between the two cars that were traveling opposite directions. And we satisfied the terms. My answer has A naught in it and T naught. On to part C. So part C is going to ask us to graph something, and we're going to have to graph velocity versus time. Now, hopefully, as I get over there, you're remembering, oh yeah, a VT graph, the slope of a VT graph is acceleration. I hope you said acceleration. And it makes sense. What's slope? Slope is rise over run. And what are we looking at for our rise? Well, it's velocity. And what's our run? It's time. So isn't velocity over time acceleration? Rise, velocity over run, time, that's acceleration. Okay, I think you get it. Let's go over to the paper and graph. Oh, we should read part C first, right? Sketch and label a graph of velocity of each car as a function of time. And we want to make sure our graph ends at time T naught. And since they're not asking us to actually assign values to these different hash marks, we can just sketch a graph. And I know that I'm dealing with a constant acceleration. And so there is, just like that, that is car A's graph of acceleration. Does that make sense? So for every unit of time that passes, I speed up by an equal amount of velocity. And that's what it means to have a constant acceleration. And therefore, I have a constant slope. Now, what about car B? Car B had half the acceleration, but it was also a negative acceleration. So that means that I wouldn't have a positive slope, I'd have a negative slope. So half the steepness, by the way, this is 5 boxes tall here for car A, so that means I'd want to go 1, 2.5 boxes for car B, and it would look something like that. And make sure on your actual graph paper, you really get to that 2.5 mark. That's what you want. So this is car B. Done. We're done with part C. We didn't have to do anything other than to sketch these accelerations. And again, the second you choose that as the acceleration for car A, meaning the steepness of that slope, this slope has to reflect half of that steepness. Okay, on to part D. Let's check that part out. So part D is going to ask us which car goes further, which seems like a silly question because we already showed in part A, clearly car A goes further and car B went, half as far by the end of the 4 seconds. But specifically, they want us in part D to justify our claim by using evidence from the graph sketched in part C. Obviously, car A goes further than car B, so you check this off. And how would you justify it? Well, going over to my graph again, I can easily justify it because the area under a curve is the displacement that you go. And in this case, we're saying distance. So the area under the curve for car A is all of that stuff that I just shaded. That's a much bigger area than this shaded area for car B. So after I check the box that car A went further than car B, I would simply say the area under the curve for car A is bigger than the area under the curve for car B. Since the area under the curve is the distance, car A goes further than car B. That's all you got to say. All right, make sure to like, subscribe, and ring that bell because I'm pushing out more of these questions every single week. Have a good day.